Ever use your phone to unlock with your face? Or scroll through a highlight reel that AI somehow knew you'd love? We take this step for granted, but what's wild is how much of it traces back to dot physics. And not just any physics, but this year's Nobel Prize-winning stuff.
It's true, and we're not talking about your typical high-tech gadgets here. This story starts with scientists trying to understand the brain but using the tools of physics, not biology, as you might expect.
Okay, now that's a curveball. So we're
Yeah.
talking about the link between how our brains work and magnets.
Exactly. Well, sort of. See, back in the 1940s, computers were these giant calculators. Powerful, sure, but about as good at recognizing a pattern as a potato. Scientists knew that for machines to truly learn, they needed a way to mimic the brain's ability to see connections and make sense of messy information.
Right, because humans do this so effortlessly. Recognizing a face, understanding speech, it's almost instinctual.
And yet incredibly complex. Early attempts to program this kind of learning into computers were like trying to build a skyscraper with toothpicks, technically possible, utterly impractical.
So where do our Nobel Prize winners come into all of this? Give us the heroes of our story.
Enter John Hopfield, a physicist who looked at how magnets behave and saw a surprising connection to the brain. In 1982, he unveiled his Hopfield network, a model for how neurons might store and retrieve information.
Hold on, magnets, neurons, how does that even work?
Think of a bunch of tiny magnets scattered randomly. Each magnet can point up or down, like a tiny switch being on or off. Now imagine these magnets are all connected, so one flipping influences all the others. This messy system, believe it or not, is surprisingly good at storing patterns.
Okay, I'm trying to wrap my head around this. So each magnet is like a neuron in the brain, and the connections between them are like synapses.
Precisely. Hopfield's big insight was that you could represent information, like an image, for instance, by tweaking which magnets are pointing up and which are down. The network then remembers this pattern by adjusting the strength of the connections between the magnets.
So it's like each magnet is a tiny piece of the puzzle, and the connections are what hold the whole picture together.
And here's the really clever part. Because of the way these magnetic interactions work, the network doesn't need a perfect copy of the image to recognize it. It's more about finding the closest match, even with some parts missing or distorted.
Wait a minute, so it's not just about rote memorization. It's like understanding the gist of something, even with noise and errors. That seems incredibly powerful,
Yeah.
especially when you think about how messy real-world data can be.
Absolutely. Think about a computer trying to recognize a face in a crowd. The lighting might be bad, the angle weird, but our brains don't even flinch. Hopfield's network brought computers one step closer to that kind of flexible, human-like understanding.
This is blowing my mind. We've gone from magnets to minds in like 5 minutes. But if Hopfield cracked the code on how machines could remember, what's next? Because remembering is just one piece of the puzzle, right?
You're exactly right. Recognizing a pattern is one thing, but understanding its meaning, its context, that's a whole other ballgame. And that's where our second Nobel laureate, Geoffrey Hinton, picks up the story.
All right, lay it on me. What was Hinton's big breakthrough?
Hinton was obsessed with this question. How do brains, or machines for that matter, go from recognizing a pattern to actually understanding what it means?
It's like the difference between knowing all the letters of the alphabet and actually understanding a Shakespearean sonnet.
A perfect analogy. See, Hopfield's network gave us a glimpse into how machines might store information, but it didn't quite explain how they could learn their own categories, their own internal models of the world. And for that, Hinton turned to a rather unexpected source, 19th century statistical physics.
Okay, now this is where I usually start to get lost, but I have a feeling you're going to make it fascinating. Statistical physics and brains, walk me through it.
In 1877, a physicist named Ludwig Boltzmann figured out a way to describe the probability of finding a system, like a bunch of gas molecules, in a particular state. It's all about energy and how it tends to spread out.
Okay, I'm vaguely remembering something about entropy from high school physics. But how does this relate to teaching computers how to learn?
This is where Hinton's genius really shines through. He realized that you could use Boltzmann's ideas to describe not just molecules, but also the way neurons in a network interact. Imagine each neuron is flipping between on and off states, just like those magnets in Hopfield's model.
So instead of describing the energy of a gas, we're now talking about the probability of a certain network configuration, a certain pattern of neurons firing.
Precisely. Hinton's breakthrough, what he called the Boltzmann machine, was a way to use these statistical ideas to train a network to recognize complex patterns. It's like taking a network and showing it tons of examples, say pictures of cats and dogs.
And the network is figuring out, based on the probabilities of certain features appearing together, what makes a cat and a dog.
Exactly. The network is essentially learning the underlying statistical structure of the data, even if it can't explain it in words. It's like if you showed a Boltzmann machine enough pictures of Van Gogh paintings, it could probably start generating its own Van Gogh-esque images, even though it doesn't understand brushstrokes or artistic intent.
Wow, that's both amazing and a little creepy. But if this was all happening back in the 80s, why weren't we all hanging out with robot buddies by the 90s? What happened?
You've hit on a major roadblock. These early neural networks, while powerful in theory, were incredibly computationally expensive to train. Imagine trying to run a marathon on a treadmill that's also trying to calculate pi to the last decimal. It's going to take a while and probably overheat.
So we had the blueprints for a superbrain, but not the computing power to actually build it. But Hinton, ever the optimist, he didn't give up, did he?
Of course not. Hinton and a handful of other believers knew that this was more than just a temporary setback. They understood the potential of neural networks, even if the technology hadn't caught up yet.
They were like those early internet pioneers who saw the potential of the World Wide Web before anyone else did.
Exactly. And just like the internet revolutionized communication and information sharing, Hinton's work would eventually revolutionize artificial intelligence. But it wouldn't happen overnight.
So what was the missing ingredient that took neural networks from intriguing theory to world-changing technology?
The answer, in a nutshell, is deep learning. Remember how those early networks were limited by the sheer complexity of training them all at once?
Yeah, it was like trying to teach a kid the entire alphabet, grammar, and literary theory, all at the same time, a recipe for disaster.
Precisely. But what if, instead of tackling everything at once, you could break down the learning process into smaller, more manageable steps?
Kind of like building a house brick by brick, layer by layer, instead of trying to sculpt it out of a giant block of concrete.
A fantastic analogy. And that's essentially what Hinton and his collaborators figured out in the mid-2000s. They developed a technique for pre-training deep neural networks with many layers, one layer at a time.
And I'm guessing this pre-training idea had something to do with Boltzmann's statistical mechanics.
You're catching on. They used a simplified version of the Boltzmann machine to train each layer of the network separately, giving it a head start on understanding the features and patterns in the data.
So instead of overwhelming the network with all the complexities of the task at once, they were essentially giving it a step-by-step education.
And it worked. This breakthrough, combined with the exponential growth in computing power, unleashed the full potential of deep learning. Suddenly, we could train networks with hundreds, even thousands of layers, each layer learning increasingly abstract and sophisticated representations of the data.
So we went from those clunky early networks that struggled to recognize a handwritten digit to AI systems that can diagnose diseases, translate languages, even compose music.
And let's not forget, it all started with two physicists looking at magnets and molecules and seeing a connection to the inner workings of the human mind.
It's like that old saying, the more we learn about the universe, the more we realize how much we don't know.
And in this case, how much more we can discover with the help of these incredible tools that physics helped to create.
This has been incredible, but I have a feeling this is just the tip of the iceberg. You mentioned earlier that AI is now changing how we do physics itself, which is mind-blowing. You're absolutely right about that. It's like physics gave AI its first brain, and now AI is returning the favor by giving physics superpowers. So tell me more. How is AI actually being used in physics research today?
Let's take something called protein folding as just one example. Imagine trying to figure out the 3D structure of a protein, which essentially determines how it behaves in the body. It's like solving a ridiculously complex 3D jigsaw puzzle in the dark. For decades, this was a painstakingly slow process, even with supercomputers on the job.
I vaguely remember reading about this. Didn't some AI system recently crack the protein folding problem wide open?
Exactly. It was a huge deal. AlphaFold, developed by Google DeepMind, used these very principles of deep learning we've been discussing to predict the 3D structure of proteins with incredible accuracy. And here's the kicker. It can often do it in minutes or hours compared to the years it used to take.
Minutes versus years. That's insane. What kind of impact is this having on actual research?
It's a game changer, honestly. Knowing the shape of a protein is crucial for developing new drugs, understanding diseases, even engineering new biomaterials. AlphaFold is like handing scientists the blueprints to the building blocks of life. It's already accelerating research in fields like medicine, agriculture, and even environmental science.
It's amazing to think that we're talking about AI, not just making our phones smarter, but actually helping us solve some of humanity's biggest challenges.
Absolutely. And that's just one example. AI is being used to analyze the massive amounts of data coming from telescopes, giving us unprecedented insights into the early universe and the formation of galaxies. It's helping design more efficient solar cells, develop new materials for energy storage, even model the effects of climate change with greater accuracy.
So while some folks are out there worrying about AI becoming Skynet, others are using it to push the boundaries of human knowledge.
And that's important to remember. This technology, born from a deep curiosity about the universe and the human mind, has the potential to do so much good in the world.
You know, it's funny, every time I use facial recognition to unlock my phone, it seemed like magic. But now I'm realizing it's not magic. It's physics, it's math, it's the culmination of decades of research by brilliant minds like Hopfield and Hinton who dared to see connections nobody else saw.
And let's not forget all the researchers, the engineers, the countless others who toiled away, building on these foundational ideas, pushing the boundaries of what was possible.
This deep dive has been a wild ride. We started with magnets and somehow ended up at the frontiers of AI and its impact on, well, everything. So the next time you ask Siri a question or watch an AI-curated video playlist, remember that it all goes back to fundamental questions about how the universe works. It all goes back to physics.
And the story is far from over. Who knows what incredible discoveries await as AI continues to evolve, and we continue to ask those big, fundamental questions about the nature of intelligence, the universe, and our place in it.
Something to ponder for sure. Thanks for joining us for this mind-bending deep dive. Until next time, keep those synapses firing.